The second paper is from National University of Kaohsiung. It's local, yeah. Let's welcome the Professor Zhong Xin Wu and his student Pu Xu. The title is Cost Effective and Reliable Cloud Storage for Big Data. Let's welcome.
Okay, ladies and gentlemen, it's my honor to be the second presenter of this session. And also I'm happy to have a talk before the keynote. But actually I'm very happy to be the second presenter to the Dr. Wei because many of our works are related work. Okay, and many of the fundamental concept was already introduced by her. So I'm easier to present our work. Okay. Our work is to develop a framework for the cloud storage for big data. But our major focus is focused on the cost effective. Okay, and the major problem we want to be was to considering the remote backup. Okay, okay. Actually, I work with based on the Hadoop distributed file system, just like the presenter Facebook and Microsoft has some improvement on this Hadoop distribution. Basically, we propose a pair block from two machines, and they are also apply the ratio coding to generate redundant blocks. But part of the parity block was are distributed to remote sites, not only for local. Okay. For the cross storage, basically, just like Dr. Wei has introduced. The size of big data set was usually beyond the commonly available machines. So usually we will integrate, connect hundreds or thousands of machines to provide the storage, And usually the efficiency and the reliability is very important. Yeah. So we will skip this. But the main purpose we are considering network partition, not just a node bag, but also network bag. Okay. For example, just like the previous talk given by Dr. Wei, if the local machine, the local network is disconnected, the user cannot access the internet. I think this is the most common problem recently. The Facebook or other internet service. Sometimes when there are several value was reported. Most of them are based on network value, not just node value. Node value is fine, just as several users was affected. But for network values, many people will be affected. Okay, so there's a different problem that we want to address. Okay, for Hadoop HDFS, Hadoop distributed file system. Usually they use replication, just in the previous. So usually Hadoop files will use triplicate replication to improve its availability. And one of the main advantage of this solution is that it can reduce the file read latency. Since it has 3 copies, so they can be accessed concurrently. Okay, simultaneous. For example, node 1 access the first copy, and node 2 access the second copy, and node 3 access the third copy. So they can be accessed concurrently. Okay. However, there's a main disadvantage. There is a high storage cost. Okay. So one data will have 3 copies. So the storage cost is free. And the other problem is that there are high information leakage risk. Any one of the three replicate, if hacked or cracked, the user's the data will be stored or just be have an information leakage problem. Okay. So to improve this problem, usually erasure coding was proposed to improve the availability, just like the red 5, red 6, and not only to improve the availability, it can also reduce the storage cost. Okay, for example, for the local repair LRC developed by Facebook, the repair cost will reduce 1.5. Okay, or just like the LTT caused by hardware, the storage cost is reduced to 1.5 or 1 less than 2. Okay. However, the main challenge is that the remote backup was not integrated into the design of the cloud storage. So if the data center of a local site was network partition, user cannot access the data. So this is the main problem we want to address. In our proposals, we enhance the Hadoop supervisor and develop the SHDFS. The main idea is that we just use two blocks. Okay, two blocks for erasure coding. Okay, but we support the remote backup. Then is the remote backup is for erasure coding parity block, not for the original data block. Okay, and we will explain two blocks is enough. Okay, and we propose two backup models. They can support erasure coding and remote backup together. Okay, and we analyze the performance. This is a related work. Since we've already this part has already been introduced by Dr. So I skip this. The main part is the storage cost and the recovery cost. The recovery cost is just like a table traffic. It's many big issues in cloud storage, but it's not a focus of our research. Okay. In Hadoop, usually there are one data node and a many data node. And this is a common placement for the data block. Usually, for example, the block 2 will be, this is a one data node. There are 8 data nodes, and this data block will be placed here, 1, 2, 3. Okay, usually there were 3 replicates, but sometimes there are these, probably there are only 2. Probably one is lost or is undergo to be replicated, not finished yet. Okay, so usually the replication factor is 3. Okay, this is a storage cost. Okay, so to reduce the storage cost, Hadoop propose another solution just like Hadoop, which is RAID. Okay, apply the RAID technology to the Hadoop system. 2 models have been proposed. One is SOR, just use SOR operation. Okay, and the other one is a read-solving scheme. For SOR, usually for both schemes, they will access 10 source block to generate the parity block. For SOR, you will 10 source block to generate 1 parity block. So it can reduce the storage cost to 1.1. However, to improve the reliability, they suggest to replicate the whole blocks, including the 10 source block and one parity block. So there will be 22 blocks in total. So the storage cost becomes 2.2. And for resolving scheme, sorry, they suggest 10 source block to generate 4 parity blocks. So there were 14 blocks in total. The storage cost is 1.4. This is the most common used in most online cloud storage. However, the problem, the more bigger problem, if the data center was level partition, we cannot access the data. Okay, since most of them will be kept in local. Okay, so two problems here. The first is they need to access the block to generate the parity block. This will be heavy network traffic, even during the creation or the repair of the parity blocks. Okay, the second problem is the multi-gap issue. Okay, so we first review three generic model for the problem. Okay, the first one is the hour-based model. This is just for comparison. Actually, there are no data here. So for each data, we usually store in one set. For cloud storage, there are more than one host. This is most case, two hosts, two nodes, T1 and T2. They each have one block, assume one block. But here we assume the X node is the local network, and the X axis is the global network. Okay, this is the R2 duplicate model used in the SOR, Hadoop RAID SOR scheme. Okay, for this is a local site, this is a remote site. We can simply replicate the data into the remote. So P3 has one replicate of the P1 node, and P4 has one regular P2 node. So when the node fails, or the whole site value, network partition, okay, the outside can still access this data. Okay, this is the simplest application model. Okay, the simplest model to support the data. There's one good thing is that the minimum storage cost for this is just 2. This is the minimum. Why? Because if this is failed, okay, this is support. This can be accessed. If this was network partition, we can access it. So anytime there is one complete copy of the data can be accessed. Okay, so this is the minimum storage cost. If you have the storage cost below 2, we usually you cannot guarantee the data can will be always online. Okay, so this possible is implementation storage. For example, the data center, local data center, remote data center, and we implement the local venue, local switch, and each server. Okay, we can fully duplicate this whole data center to the remote. This is the simplest approach for most common systems. Okay, this is the R3 triplicate model used in original Hadoop distributed file system. There are 3 copies for each block. For example, we can for block 1, we can have one remote backup in P5 and one local backup in P3. Okay, this is the original design of the Hadoop distributed file system. This is good for reliability, but the main problem is that the storage cost is quite high. The storage cost is free. This is the problem. Okay, so to reduce the storage cost, we just described the Hadoop RAID need a 10 source block. Okay, and any update to one of the source block would need to regenerate the parent block. So this is why the Facebook and Microsoft proposed the LRC, local repair code, to reduce the local traffic. And there's one part is that any virtual machine with a source block will initiate a data recovery process. Okay, to regenerate the original source block or to generate the parent block. So we propose E42 or E52. Okay, we only use 2 source blocks to generate the parity block. Okay, the storage cost will be 2 and 2.5 respectively. Okay, in our proposed E42 collecting code model. Okay, the local copy is here. For the remote backup, this backup was used erasure coding to generate this 2 block, Q1 and Q2. Okay, so the most interesting is that for each one of is fair, no value. For example, if block 1 is fair, it's value, it's fair. We can access one of Q1 or Q2 to recover the B1 with the half of B2. Okay. This for erasure property, any two of the 5 blocks, any 2 of 5, we can recover the original one, either B1 or B2. So we can recover B1 and B2. For example, this is the level partition. We can recover B1 and B2 from Q1 and Q2. Okay, we can recover B1 and B2 from Q1 and Q2. So the user can continue to access the data from here. So if this one is any one of B1 or B2 is lost, we can recover it from either B1 or B2 plus one of them. Okay, this is the main design concept of E42. So the storage cost is 2. This is the minimum storage cost. It's a minimum storage cost. And another good thing is that it prevents the data leakage because this is not the same as B1. This is not the same as B2. Either P3 or P4 cannot recover the data if they have the other one. They need 2 blocks to recover data, but they only have 1 block. Both of them only have 1 block, so they cannot recover the source data. So we can prevent the information leakage problem. Okay. However, to recover the original data, for example, when the P1 is lost, to recover the B1, we need to access the remote, either Q1 or Q2 to recover the B1. Okay, so we have a remote network access. To reduce this traffic, okay, we introduce the E52 collective model. Okay, now this is very simple. Just keep 1 more parity block local. Okay, so we can have 3 parity blocks, 2 source blocks to generate 3 parity blocks, 2 in remote and 1 in local. And based on the ratio code, okay, any 2 of 5, we can recover original 2 blocks. Okay, either this one, B3 and Q1, we can recover B1. So B1 and Q1 to recover B2. Or Q2 and Q3 to recover E1 and B2. Okay, so when any one of our local site is failed, we can recover the other one from P3. Okay, so we don't need to access the report. For single value, we can recover it locally. This is the main idea of the E52. Okay, so however, we introduce 1 more parity block, so the storage cost becomes 2.5. This is a problem. I think it's okay. Since you to support remote backup, you need 2. Okay, to support remote backup, the minimum storage cost is 2. So probably you have one more block to support remote backup. Okay, so it's generalized. So you may say, why just 2? Okay, probably 3 or 4. Is it okay? Yes. Actually, in theory, it's okay. It's okay. You can have any design of 2n plus 1. And that means for any 2n plus 1 block. Okay. For any n block, for example, 2 block in our case, you may have 10 blocks. Okay, just like a Hadoop rate. Access 10 blocks and to generate 2n plus 1. Okay, to generate 11 parity blocks and 10 source blocks. So there are 21 blocks in total. It's okay, you can have the same design. Okay, so for this design, you can 10 parity block in remote or n block in remote. Okay, and n source block in local. To support local recovery, of course, you can have only 1 local parent, 1 local parity block in local. So that's why we need 2n plus 1. Okay, 2n plus 1. But the main problem is that as the n increase, you say 10, why not 100, why not 1,000? Okay, then it's clear that as the n increase, the loss or update over any one of them will trigger recovery. So the network traffic will be pretty high. Okay, so the good balance is that we think 2 is good enough. In theory, 2 is good enough. It's simple. It's simple. Just as a 2 block to generate the parity block. So it's a simple design. Okay. Okay. So how to implement? In this paper, actually we did not specify any. You can use any common ratio code to implement our model. For example, for reason code, the original design was 1517. You can set the you can assume the other blocks are constant. Okay, the other constant block and the two block, the source block. This is a simple case design. Okay. For the linear symbolic combination, you can generate the parity block by just subtract and one addition, one subtract and one addition. So for the third block, we can use just like this block 1 plus 2 multiply block 2. Okay, but for the Ruby transform code, just like the SOR operation, we have a more complicated design, just like this suggestion. For this core evaluation, we have another paper on this issue. Okay, this is a simple evaluation. We assume all nodes have the same reliability for value range. Okay, each node have the same reliability, and the local network and the remote network have the same network reliability. In this case, we default set to 0.999. Oh, okay, 39. And we assume the global internet is always alive. Okay, the global internet will not disconnect. This is a simple comparison, the 5 model we just presented. For the R2 and the E42, we have a minimal storage cost. Okay, and for the E52, we have a small storage cost than the R3. And we can tolerate 2 node values just like the R3. But E52 can tolerate 3 node value, and these 4 schemes have a remote backup, so they can tolerate the network partition. Okay, and this is the case when the network is partitioned and there is one more node value. They happen together, node value and the network partition. R3 and the E52, they can tolerate this case. And the proposed method can support to prevent data leakage. Since the block was called erasure coordinate, not the original source block, so the site have a parity block cannot recover the data if they don't have a more block. Okay, this is a reliability evaluation. This is a genetic test for single machine, and this is the 3 model. Which are under signal very low, since we multiple disks many more node will be accessed. So usually the reliability will stay the standard line. Okay, as the node reliability increase, okay, you can see the E52 perform better than the R3 is R3, and the E42 is perform better than the R2. Okay, the main reason is that 1 terabyte block can help recover over the other 2 blocks. Okay, this is the main reason we can improve reliability. And usually the reliability is pretty high, so we further simulate a higher node reliability from 1 failure from 1 node to 0.59. In this case, we can see this is the line for E52, and this red line is for E42, and this is R3. Okay, the R3. Okay, we can find that during the high node reliability, the E42 performance is better, very close to the R3. Even if it has just the storage is 2, but the R3 storage is 3. Okay, so we believe it is a very cost-effective solution to support balance reliability and storage cost. If you want a better reliability, E52 is a good suggestion. Since you can under the high no reliability, it performs about 10,000 times better than the R3. Okay, this is a simple simulation result. Okay, in conclusion, in this paper, we propose two models to support remote data as well as the erasure code to storage, to reduce the storage cost. In the proposed E42, the storage cost is minimal. And for the E52, the storage cost is 2.5, but it can perform 10,000 better than the R3 model. Okay, and we show that two-source block is a simple and useful approach to support cost-effective and reliable cloud storage. Okay, this is my talk. Thank you.
Okay, any question for Professor Wu? Okay.
It's a very interesting idea.
Thank you.
I have a question about performance. Right? So when you do a write operation, I think you can do a lot of write operations compared to the traditional one, right?
Yeah, that's
If you
correct.
do the performance comparison, not reliability, I mean the performance,
Performance,
right?
right.
Performance. Did you do compression?
We have just some analytic model. We access the right assets,
Right.
but we have not a real simulation, not just a real evaluation. We have an analytic model. If you want to, we can show you. This is the work of our master students. They will complete analysis for the performance. Okay.
Thank you.
Very good question.
Okay. I think due to the time limit, just give you a big hand to our Professor Wu. I think that's a very nice work.
Okay.